I'm Grishma and you're watching my channel G Tutorial. Today's class is on logic gates. The basics of logic gates have been discussed in the previous class. In today's class, we will see Nand Gate and NOT Gate as universal gates and some problems with it. If you like my channel, please subscribe to my channel for getting more RRB J related videos. Now let us get to a portion. First, let us see the Nand Gate as universal gate. The symbol for Nand Gate is this. If you are giving A and B as the input to a Nand Gate, its output is AB bar, A dot B bar. And the truth table is, it provides output 1 for all inputs except both inputs as 1. So, we can see how we are implementing other gates using this Nand Gate. First, let us see the NOT Gate. If you have giving the input to a Nand Gate like this, that is, to both terminals we are giving the same input, then we will obtain a NOT Gate. That is, we will obtain A bar at the output. We can see how this happens. If you are feeding the same input, if you are feeding when A is equal to 0, let us see the case. When A is equal to 0, the output of both inputs are 0 and 0. So the output is what? 1. So what is actually done? It is just complementing the output. So we can say that it is a NOT gate. When both inputs of a NAND gate is fed with the same input, we obtain a NOT gate. Next is AND gate. Actually, the output of a NAND gate is AB bar. If we are providing a NOT gate at the end of this output, we will get an AND gate now. So, at the output of a NAND gate, we are providing a NOT gate, and NOT gate is also implemented using NAND gate. Then we will get what? Here the output is AB bar, then AB double bar. AB double bar is actually AB. That is, we obtained a NAND gate, AND gate. Next is OR gate. We are complementing A, that is, we are providing a NOT gate at A and B. So we will get A bar and B bar. Then we are ANDing it. A bar dot B bar the whole bar. This is the output of NAND gate. On solving that, A double bar is A. Complement of dot is plus. B double bar is B. We can obtain an OR gate. Next is XOR gate. We are we are providing A and B to the input of this, so we will get AB bar, and along with that we are providing A also. So output of this gate is A dot AB bar the whole bar, and here AB bar, B dot AB bar the whole bar. Its output is provided here. So it will be A dot AB bar whole bar the whole bar. This is the output of this NAND gate. What you have to obtain an XOR gate. XOR gate is A bar B plus AB bar. Let's solve this. We are taking double complement of this. So double complement, we are splitting this first. This outer complement. So double complement occurs over here and here, and this complement of dot is plus. Then double complement A double bar is A itself. So we will obtain this as the answer. So A dot A bar B, no, AB bar plus B dot AB bar. We can solve this. This is A dot AB the whole bar is A bar plus B bar. Similarly, here also A bar plus B bar. A dot, now we can open the bracket. A dot A bar is 0. Similarly, B dot B bar is also 0. So A dot A bar is 0 plus AB bar. Next term is B dot A bar is B A bar plus B dot B bar is 0. So this is the answer. That is actually A B bar plus A bar B, which is the output of XOR gate. So we have implemented XOR gate using NAND gate. Similarly, XNOT gate is a complement of an XOR gate. If we are providing a NOT gate at the output of XOR gate, we will get a XNOR gate. So the same circuit we are providing a NOR gate. NOR gate is implemented using NAND gate. So this is the AB plus AB bar. Sorry, A bar B bar. This is the output of XNOR gate. We are complementing this output. Okay. Now let us see how to implement all basic gates using NOR. That is NOR as universal gate. This is the symbol for NOR gate. When we are feeding A and B at the input of NOR gate, we will get output as A plus B the whole bar. The truth table for this is it provides output 1 only when both the inputs are 0. Now we can see how to implement all the basic gates using NOR gate, or how NOR gate acts as a universal gate. So NOR gate implementation using NOR gate. When we are feeding both the inputs of the NOR gate with the same input, we will get a NOR gate. When both inputs are 0, output is 1. When both inputs are 1, the output is 0. This is this is how we are implementing NOR using NOT. NOT using NOR. Next is AND. This is how we implement an AND gate. We will get A bar at the output. Here we will get B bar at the output. A bar plus B bar the whole bar. This is A dot B. Next is how we implement OR gate. The output of this gate is A plus B the whole bar. When we are complementing it, we will get A plus B the double bar, which is equal to A plus B. Thus we obtain an OR gate. Next is XOR gate. Here we will be getting A plus B the whole bar, A plus B the whole bar is provided, B plus A plus B the whole bar, and it is fed to this gate, and we will get A plus the whole bar. Here, so there is a bar. On solving this, we will get the output as A bar B plus A B bar, which is the XOR gate. When we are feeding a NOT gate at the output of this, we will get XNOR gate. And we are implementing the NOT gate also with NOR gate. Then we will get the output as A bar B bar plus AB, which is output of XNOR gate. This is how we are implementing all basic gates using NOR gate. So let us see the equivalent symbols for all gates. These are the equivalent symbols you can note down. For an OR gate, we are using this equivalent symbol. Here A is this denote the complementation process. That is, A is complemented, B is complemented, and is provided to a NAND gate. And the output will be A plus B, which is the output of OR gate. So OR gate and this circuit is equivalent. Similarly, AND and this circuit is equivalent. Similarly, you can note down all these. These are the equivalent circuits of these gates. Now let us do some problems based on how NOR and NAND are act as universal gates. This is the first question. Find the minimum number of NAND gate required to implement the logic expression. This y is equal to A plus AB bar plus AB bar C. We are asked to find the minimum number of NAND gates. So we have to reduce the expression. Let us reduce it. From here and here we can take AB bar common. So AB bar into 1 plus C. 1 plus C is 1 plus anything is 1. So A plus AB bar dot 1. This is 1. AB bar dot 1 is AB bar. From here we can take A as common. Say A into 1 plus B bar. 1 plus B bar is again 1. So A dot 1 is A. So the reduced expression of Y is A. Here for implementing A we do not require any gate. So the number of gates, NAND gates required is equal to 0. We do not require any gates. Next question. This is the next question. Find the minimum number of NAND gates to implement the logic expression y is equal to a plus bc. In the previous question, it was very easy question. We were able to find the number of gates easily, but in this case, you have to follow these steps to find the minimum number of NAND gates to implement this. First step is we have to realize the given expression. First, we have to reduce the given expression, but this is in the reduced form or minimal form. So again, we don't have to do anything. First step is realize it using basic gates, that is OR, and NOT. Then bubble at the output of AND gate and input of OR gate. I will show you. First step is you have to implement this using basic gates. BC is B and C. Its output, and A is performing an OR operation. We will get Y as the output. In the second step, bubble the output of AND gate. Output of AND gate is bubbled and input of OR gate. So here and here we are bubbling. But here check, you are feeding A to this bubble, then you are feeding A bar. It should not be the case. A has to be fed. So if we are putting a bubble over here, what is actually fed to the input of this gate? A bar is again complemented. So A double bar, A is fed. Now we can implement this using the NAND gate. This is replace all gates with equivalent NAND gate. So first, if we are complementing this, we can replace that using a NAND gate now. So this is the first NAND gate. Then equivalent of this is a NAND gate. Then B and C is also fed to a NAND gate. This is the output. So the minimum number of gates to implement this expression is 1, 2, 3. 3 gates. 3 NAND gates is required to implement this. I will explain it once again. This is our question. Y is equal to A plus BC. If it is not in the reduced form, you have to reduce it. Then realize it using basic gates. This is our basic circuit. Now we have to bubble the output of AND gate and input of OR gate. So we are bubbling the output of AND gate and input of OR gate. If any of the input is fed directly to this OR gate, you have to bubble it again. Otherwise, A bar will be fed to this gate. So you have to bubble it again. Okay, this is only what is required. This is a NAND gate. This has already become a NAND gate. This is the equivalent of a NAND gate. I have given the equivalent symbols before. This is an equivalent of NAND gate, and NOT also. This is NOT operation. This NOT operation can also be implemented using a NAND gate. So we are replacing all the gates with equivalent NAND gates. Replacing this bubble with a NAND gate. This is NOT operation. Next, this has already been a NAND gate, and this is an equivalent of a NAND gate. So now we can count the number of gates. The 3 gates required to implement this expression. Next question. The next question. Find the minimum number of NAND gates required to implement the logic expression y is equal to x bar plus y dot z plus w. So first step is we have to minimize it. Then realize using basic gates. Bubble. First step we can write. So x bar is, we are providing a NOT gate. Y bar is this. This is x bar. This is y bar. And we are performing an OR operation. And Z and W again we are performing an OR operation. And the output of this is fed to an AND gate. AND gate, sorry. AND gate. Next step is bubble the input of OR and output of AND. Output of AND and input of OR has to be bubbled. Okay. But if we are doing in this way, we will be using, here there will be, in next step we have to convert this to equivalent NAND gate. So there will be NAND gate here, 2, 3, 4, 5 NAND gates will be used. But we are asked to find the minimum number of NAND gates. So let us check the expression. Let us rewrite it in some other form. So the expression y can be written as y is equal to x bar plus y bar. It is actually x by the whole bar, no? It is equal to x bar. If you are opening the complement, x bar x bar plus y bar. So this can be rewritten as this into z plus w. So it will be x by the whole bar into z plus x by the whole bar into w. Okay. Now we can implement using basic gate. X5, this is actually an AND gate. Then we are providing this X5, this output to NAND gate. So here is an AND gate. Then the output of this is also fed to another AND gate. It is added with W. The output of both of this is fed to an OR gate. Now we are performing bubbling input of OR and output of AND. Input of OR and output of AND. Okay. Now we can replace using equivalent AND. These three are actually AND gates. We can replace this. This one is replaced by an AND gate. Now the number of NAND gates used to realize this is 1, 2, 3, 4. So 4 number of gates is required. We are always asked to find the minimum number. You have to keep that in mind. So always try to reduce the expression before going to implement. There will be some tricks hiding in each and every question. You have to analyze that before doing the problem. Next question. This is the next question. Find the minimum number of NOR gates to implement this logic expression. If you are asked to implement using NOR gate, the expression should be in product of sum format. So the first step should be you have to convert this in terms of product of sum expression. This should be kept in mind. If it is not, you have to convert to post expression. So the expression will be, you can use distributive law. A plus B dot C, which is actually A plus B, A plus C. This is the actual expression for this. So we obtain the post expression. Now we can implement using the basic gates. So A, B, we are taking the OR operation here. A and C, we are taking the OR operation. Then we are ANDing it. Now the second step is bubble. In previous case, we are bubbling the output of AND and input of OR. But in this case, when implementing using NOR, you have to, when NOR is used to implement, you have to bubble the output of OR and input of AND gate. Now we can represent using equivalent gate. Equivalent NOR gate. So this is NOR gate, and this is the equivalent of NOR gate. So this is our expression. This is our circuit AC. Again a NOR gate. So the number of gates required is 3. 1, 2, 3 NOR gate is required to implement the circuit. Next question. This is the next question. Find the minimum number of 2-input NAND or NOR gate to implement the logic expression f of ABC is ABC bar. I am using NAND gate, 2-input NAND gate to represent this. So first let me represent this using the basic gates. So I should use only 2-input gates. So I am using 2-input AND gate. I will be getting output as AB. Then with another 2-input gate, I obtain ABC. Then if I am providing a NOT gate, we will be getting ABC bar. Now I am transforming each of the gates to NAND gates. I am bubbling the end of AND gates. There is no OR gate. So it will be A, B. This is an AND gate. This is another NAND gate. And the NOT gate can be converted to NAND gate. So the number of NAND gates required to implement this expression is 3. 3 2-input NAND gates is required to implement this. Next question. This is the next question. We are asked to find the output Y of the logic circuit. This is the logic circuit. P, Q, R and S are the inputs. We are asked to find the output Y. What we have to do? Let us find the equivalent for each of this. If you are considering this much portion, we can see that it is the equivalent of an OR gate. So, when P and Q are given as an input to an OR gate, the output will be P plus Q. This is a NOR gate. This is equivalent to a NOR gate. So, P plus Q bar. Similarly, this is also an OR gate. So, R plus S. It is complemented and it is fed to this gate. So, P plus Q bar, R plus S bar, it is fed to a NAND gate. So, P plus Q double bar is P plus Q. Complement of AND is OR. R plus S double bar is R plus S. So, the answer is P plus Q plus R plus S. Y is equal to this. This is the answer. Next question. This is the next question. The output of a two-level AND OR network is F. What is the output when all the gates are replaced by NOR gate? This is the question. If the output of this network is F, and if all the gates are replaced by a NOR gate, then what will be the output? So let us redraw the figure. Figure will be right. We are replacing each and every gate by NOR gate. So first let us find the output F. This is an OR gate, so output is AB, and this is again an AND gate, and if we are ORing this, the output is AB plus C. F is equal to AB plus C. If we are using NOR gate instead of that, the output is whole bar C plus D the whole bar, which is equal to plus D. A plus B double bar is A plus B. Complement of dot is complement of OR is dot C plus D. So the output we have obtained here is A plus B into C plus D. Comparing both this, we can say that the output we are obtained by replacing the gate by NOR gate is just the dual of this. That is, we have obtained dual of F. Now we can see what is meant by dual. Dual of an expression, a logical expression, is obtained by replacing each of the AND operation by OR operation and OR operation by AND. So if you are replacing this AND operation, we will get A or B. Replacing this plus or OR operation by AND, we will get dot. Again we are replacing this dot by O. So this is the dual of this, or this is the dual of this. Okay. So the answer is F dual. Next question. This is the next question. For the logic circuit shown, the required input condition A, B, C to make the output X is equal to 0. We have to find the value of A, B, C so that X is equal to 0. The output X should be 0. There are 4 options. First, let us see which all gates we are using. We are using a NAND gate, XOR gate and an XNOR gate. This is the truth table for NAND, XOR and XNOR. If the output of NAND is 0, the output of NAND is 0 only for the case when all the inputs are 1. Here I am writing only the case of 2-input NAND gate. For 3-input AND gate, the case is also same. When all the inputs are 1, then only the output is 0. So we have to obtain the output as 0. So we can see that C is directly one of the input of this AND gate. If output is 0, all the input should be 1. We are using this condition. So C is 1. So we have obtained C is equal to 1. Now we can check the options. But in the options, all the 4 cases C is equal to 1. So we have to find A and B also. Next, let us go for A and B. If we are considering this gate, we know that C is 1. So one of the input is 1. For an XOR gate, we know that input is 1 and output should also be 1. For an XOR gate, for output to be 1, one of the input should be 1 and the other should be 0. So, for this XOR gate, we know that C is 1. Only if B is 0, the output is 1. So, we have obtained the value of B also. B is equal to 0. Now, we are considering this XNOR gate. Its output is also 1. And now we obtain that B is 0. For what case the XNOR output produces 1 as output? We can check that. XNOR is an equality dictator gate. So, only when both inputs are 0 or both inputs are 1, the output is 1. We know that one of the input is 0. So, the other input also should be 0 to obtain 1 as output. So, A is also 0. So, the actual input is 0, 0, 1 for A, B and C. This is the condition. 0, 0, 0, 0, 1. D is the correct option. Next question. This is the next question. For the logic circuit shown, the required input condition to get the output Y is equal to 0. What we have to obtain? We have to obtain Y is equal to 0. These are the input conditions. Here we are using two symbols A and B. A0, B0, A1, B1, A2, B2, A3, B3 are the input to these XOR gates, and the output of that XOR gate is fed to a NOR gate. So I am just writing the truth table for XOR and NOR gate. Here I am using 4 input NOR gate, but I am just writing the case of a 2 input NOR gate to just analyze the output conditions. Now let me check. Only trial and error method using the option is possible to solve this kind of problem. What I have to obtain? I have to obtain output Y as 0. Output Y is obtained as 0 for NOR in these 3 cases. So it is not very much easy to solve this. We have to go for options. If output is 1, then if all inputs are 0, then the output is 0. But here output is 0. So all input should not be 0. Any of them should be 1. Only then, at least in some case all should be 1, or at least 1 should be 1. Only then the output will be 0. Let us use options to solve this. This number is for A and this number is for B. This is A0, this is A1, A2, A3 and B0, B1, B2, B3. So first case, A0 is 0 and B0 is 0. So 0, 0 is the input to this gate. Next is 1 and 1. 1, 1. Next is 0 and 0. Finally 1 and 1. XOR gate is an inequality dictator. When the inputs are same, the output is 0. So the output is 0, here also output is 0, here also output is 0, here also output. When all the input to an NOR gate is 0, the output is 1. So this is not the correct option. So what we have to obtain? We have to obtain at least 1, 1 from the output of this XOR gate. So only the output is obtained as 1 only when any of the gate has unequal inputs. Check. The second option is also 0, 1, 0, 1, 0, 1, 0, 1. All the bits are equal. It won't produce 1 as output. Next option is also 0, 0, 1, 0, 0, 0, 1, 0. This also not produce the output 1. So the last option is the correct one. This is dissimilar bits. We can check that. A0 is 0 and B0 is 1. So 0, 1. Next is 1 and 1. 1 and 1. Next is 0 and 0. 0 and 1. So see, when the input is unequal, the output is 1. Here it is 0, here it is 0, here also the input is unequal, so on. So any of this input has become 1, so the output is 0. These 3 cases. So this is the correct option. Here we are using XOR gate, so the input should be different. Only when the input is different, the output of this gate produces output as 1. When any of the input is 1, the output of NOR gate is 0. So we have obtained the answer. Now we have done many problems from gates. We have covered every topic from gates. In the next class, we can study about combinational circuits. If you are having any doubt, you can comment below. Thank you.